Hello everyone, welcome to the video. In this video we are going to represent the uh, qubit for a particular particle states, how qubits store the information, how we can represent the qubits, a single qubit or the multiple qubits. That part we'll discuss here. General, in case of quantum computation, the storage of information and processing of information is possible only in case of qubits. That a basic qubit representation, for example, a qubit relate to a particular state is written using the Dirac notation. The particular state is taken as psi. Here, this is represented like alpha state 0, beta state 1. This is the representation of the qubit. Here, this is representing the state 0 and this is representing the state 1. As discussed in the introduction video, the quantum computers use the superposition principle. Here, this particular particle may available in the state 0 or it may available in the state 1 or it may available in the simultaneous of 0 and 1 states. So the simultaneous representation is like alpha state 0 plus beta state 1. Here the alpha and beta is nothing but probabilities amplitude. Probability amplitude relate to the state 0 and beta is related to the probability amplitude related to the state 1. If alpha is related to the 0, that means that state is available in the the state is available in the, that means the particle is available in the state 1 because the probability amplitude for the beta is 1. If the beta is 0, that info relate to the state 0, obviously the probability amplitude relate to the alpha is 1. So, and one more condition, normalization condition we need to check. Here alpha square plus beta square must be equivalent to 1. This condition is called as normalization. See here, a qubit representing a particle state is written in this combination where psi is related to the quantum state of the particle. 0 and 1 are called as basis states. Alpha and beta are called as probability amplitude. And alpha square plus beta square equivalents to 1 is called as normalization. For example, if alpha equivalents to 1 by root 2 and beta equivalents to 1 by root 2, then state representation of a particle in qubit is psi equivalents to square root of 1 by 2 or 1 by root 2 state 0 because the probability of alpha related to the state 0 is 1 by root 2. Similarly, beta related to the probability of one state is also 1 by root 2. Here alpha is 1 by root 2 and the beta is 1 by root 2. Just I am checking the normalization condition. Alpha square plus beta square must be equivalent to 1. Here the 1 by root 2 whole square, then 1 by 2 and 1 by root 2 whole square, it is also 1 by 2. The total value is 1. So this particular qubit state is normalized. That is 50% of the probability. This alpha square is nothing but probability related to the state 0. Beta square is the probability related to the state 1. So this is the like a superposition of two basis states using Dirac notation. That is, qubit related to the particular particle state is nothing but the combination of 0 basis state and the 1 basis state. So the representation of the qubits is like this. So for example, this is a 1 qubit state. If 2 qubits, in case of 2 qubits, first we need to check what are the basis state. So obviously 0 0 is the one base state, comma 1 0 is the another base state, comma 0 1 is the another possible base state, comma 1 1 is the another possible base state. So we have 4 basis states. So then we need to understand, in case of 1 qubit, 2 states like a 0 and 1. In case of 2 qubits, we are having 4 states. So we have a formula like 2 power n number of states. Here n is nothing but qubit number. If 1 is 1 qubit, we have 2 states. 2 qubit, 2 square, 4 states. If it is 3 qubit, we have 8 states. But how we can represent that as like a psi? For example, in case of 2 states, this is take it as like psi for a particle which is having 2 qubits. Then we need to represent it as alpha 0 0, beta 0 1, gamma 1 0, and delta 1 1, as 0 0 1 0 1 1 0 and 1 1 is the 4 different basis states for the 2 qubit system. Here the alpha, beta, gamma and delta are the probability amplitudes related to the 0 0 0 1 1 0 1 1 respectively. Then normalization condition, alpha square plus beta square plus gamma square plus delta square must be equivalent to 1. Therefore, the general qubit representation is psi equivalent to alpha base state 0 and beta base state 1 for the 2 qubit system. For the 2 state system or 1 qubit. If it is 2 qubits, then the combination is like psi alpha 0 0, beta 0 1, gamma 1 0, delta 1 1 states. This is the representation of the qubit in case of 1 qubit system or the 2 qubit system. In case of 3 qubit system, we have total number of 2 power 3, 8 states like 0 0 0, 0 1 0, 0 0 1, like 1 0 0, 1 0 1, 0 1 1, or else we need to take it as 1 1 1. Similarly, we have 8 states. 1 0 0, 1 0 1, 0 1 1, 0 0, 0 1 0, 0 0 1, 1, 1, 1. Similarly, we can write it as 8 different possibilities of the particular states. Like here also one more case, 1, 1, 0. So total number of states is 8. So this is the way we can represent the qubits for a particular particle state. And the normalization is nothing but the sum of all the probability amplitudes must be equivalent to 1. The probabilities, sum of all the probabilities are equivalent to 1. Here the alpha, beta, gamma relate to the probability amplitudes. If we want to get the probability, we need to take it as square of the probability amplitude. For example, I just take it as one numerical, like psi equivalents to square root of 3 by 2 state 0 plus 1 by 2 state 1. He is asking about the find probability of measuring state 0, and he is also asking about the probability of measuring state 1. So as we know that the state 0 probability amplitude alpha equivalents to root 3 by 2, then probability is nothing but alpha square, which is nothing but 3 by 4. Whereas in case of beta point of view, here it is 1 by 2, then the probability, the beta square equivalents to 1 by 4, then alpha square plus beta square is related to the 3 by 4 plus 1 by 4, which is nothing but 1. So this particular qubit state is normalized, and the probability values are 3 by 4 and 1 by 4. State 0 probability is 3 by 4. State 1 probability is 1 by 4. Here the normalization check is also completed. So normalization, if you want to check the normalization condition, we need to take the sum of all the probabilities must be equivalent to 1. A qubit, another problem. A qubit psi is like zero point 0.8 state 0, 0.6 state 1. So the probability of 0 state is equivalent to 0.8 whole square, which is nothing but 0.64, and the probability of 1 state is equivalent to 0.6 whole square, because this is the amplitude. So amplitude square is nothing but the probability, which is nothing but 0.36. The sum of these two, 0.64 plus 0.36, must be equivalent to 1. So this state is normalized state. In this way, there is a possibility to measure the representation of the qubit state, and also there is a possibility to measure the probabilities for each state. Thank you.